Okay, so up until now we've been talking about rotational motion, but we haven't talked about what makes things rotate. Just like we did with kinematics, we first of all looked at how to examine the motion itself, and then we went on to what causes the motion. In order to make something rotate or change its rotational motion, we need a force. And the force that we have in rotational motion is called a torque. T-O-R-Q-U-E. So we're going to have a lot of talking about torque, and so you'll have to guess which one I'm talking about. Okay? All right. So to make an object start or stop rotating, a force is needed. The position with respect to the axis of rotation and the direction of the force also matter. The perpendicular distance from the axis of rotation to the line along which the force acts is called the lever arm. In this case, for force B, this will be the lever arm, RB. For force A, this will be the lever arm, RA. Let's go to an actual example. We've got a door right here, right? So if I push the door here, I apply very, very little force. But it does matter which direction I push it, because if I push it this way, the door opens. Looking down from on top, this door is either rotating clockwise or counterclockwise, right? On the other hand, if I try to push this door and close it by being very close to the hinge, I've got to apply a much larger force to make it go. So the lever arm matters, that is how far you are away from the axis of rotation, and the direction matters. You already know that longer lever arms are very helpful. Undoing bolts or doing up things which are very tight, taking them apart. Having a wrench with a long handle is very helpful. So, if we look at this, the lever arm for FA is the distance from the knob to the hinge, from here to here, or here to here, whichever one you want to call it. The lever arm for FD is 0. If there's no lever arm, if I try to push against this like this, it's not going to move, is it? If I'm perpendicular like that, I mean directly straight on going in, this door does not move, no matter how hard I try. And for FC, the lever arm is this one here. So this is the line of action for that force, and this is the lever arm that goes with it. So, we're now in a position to define what torque is. Torque is the vector cross product of the displacement from the axis of rotation and the applied force. We've already dealt with vector dot products. Who remembers where we dealt with vector dot products? What unit was it?
Circular motion?
Anyone? No? What about what is force dot product displacement? What is that called? Work, right. And in a simpler form, not taking into account the actual vector format because we actually got a scalar with work, what did we write it in general as rather than vector f dot vector displacement? We wrote it as magnitude of the force as the magnitude of the displacement times what? Right, the cosine of the angle. Now, the cosine of the angle, if the angle is 0, what is cosine equal to? 1. So, in fact, when we're doing calculations of work, the closer the force and the displacement are to being parallel, the more efficiently the work is done, right? Because that's where it maximizes, when the angle is 0. Well, with the cross product, it's actually a little bit different. Now, it's the sine of the angle that we're interested in. What is the sine of 90 degrees? 1. So this maximizes when the angle between the lever arm and the force is 90 degrees, which is what you'd expect, right? If I push against this at 90 degrees to the lever arm being that, the door shuts, right? Whereas nothing would happen if I tried to apply the same force parallel. So a cross product and a dot product are different in that way, but they're also different in another very important way. And that is, a dot product gives you a scalar. The resultant of a cross product is another vector, which is perpendicular to both of the other vectors. Perpendicular to both of the other vectors. So in this case, you can see that really what we're doing is looking for that component of the force which is perpendicular to the lever arm when there's an angle. That's given by the right-hand rule, the direction. So, what do we mean by the right-hand rule and what do we mean by direction? Well, the torque vector, the angular velocity vector, the angular acceleration vector, and the angular displacement vector all point along the axis of rotation. The question is, which direction? In this case, we're looking at somebody who's got something rotating and it's going this way, right? We say it's going up. Why? Well, if we take our right hand like this and we rotate it to follow the direction of rotation, which would be counterclockwise in this case, right? Where does my thumb point? Up. That was not a difficult question.
Sounded like a trick question.
It was not a trick question. I don't ask trick questions. Okay. All right. Now, what happens to the thumb if it was going clockwise? Tell me. Well, use your hands to figure it out. Yeah, you have to flip your hand over now, right? To make your fingers curl clockwise, you've got to put your hand down the other way. And now, which way is my thumb pointing? Down. So, you could think of it as it's spinning up or it's spinning down, right? Where have you heard those terms spin up and spin down before? Electrons, right. So, this concept of electron spin actually is a quantum mechanical concept, but what was done was that the concept was sort of borrowed from mechanics. Right? So this, if you like, is the starting point for understanding things like electrons and how they behave. Because the mathematics, when you look at the mathematics, a lot of these things look like things mathematically that we're accustomed to, like momentum, right? You can have an angular momentum quantum state, right? There's a number of quantum states for each electron. So this builds into your understanding of things like what is happening in the atom. And ultimately you take it into what is happening inside the nucleus. And ultimately you try to understand how everything works, which is the ultimate goal of physics, to have a theory of everything. Who's ever watched Hitchhiker's Guide to the Galaxy? Yeah, what is the answer?
42.
42, right. I think they were playing, that they were making a little fun of physicists there.
That's
Okay.
a good question on some of our concept quizzes.
Oh yeah, that's true. I
Yeah,
could give that one,
person
yeah.
would know you.
Okay, let's have a look at an example. In this case, we're going to use
That's wrong.
Okay, so now we're going to look at an example, in this case a biological example. The biceps muscle exerts a force, vertical, on the lower arm as shown here. Right? Here's the lower arm, here's the biceps muscle. For each case, in this case it's at 90 degrees, in this case it's 30 degrees below 90. Calculate the torque about the axis of rotation through the elbow joint, assuming the muscle is attached 5 centimeters from the elbow, as it's shown here. Now it's interesting that physical therapists usually have to take a course in physics in college so that they can understand the stresses and strains being put on the anatomy by the exercises that they're going to give to patients. Right? In the first case, we've got the force is 700 newtons. The lever arm, which is perpendicular to the force, is 0.05 meters. So the torque is the force times that perpendicular lever arm. 0.05 meters times 700 newtons, or 35 meter newtons. Not 35 Newton meters. Newton meters are a unit for energy in linear mechanics. And so to differentiate between the two, we put, say, meter newtons. If you look at a torque wrench, which is a special wrench used for tightening nuts, it will be in foot-pounds, right? We've got a measurement of length followed by a measurement of force, right? You can also get one which is inch ounces. Very, very fine torquing, inch ounces. Let's have a look at the second part. In this part, the arm is at an angle. The lever arm is shorter. In fact, if you look over here, you can see the lever arm is shorter, right? So this would have been the original lever arm here, but now it's down by that. We need to choose this angle here. And so what we find is that the perpendicular part of the lever arm is 0.05 meters times sine 60, and the force is 700 newtons. So the torque is 30 meter newtons. It's less. That is, when you've got your arm down here, down in this lower position, you don't have as much leverage. Right? It's more difficult to bring something up. Yes?
Why don't you do sine 30? Why do you do
Because we're always looking for the angle between the force and the radial part of the,
Like the x-axis almost.
yeah. It's a convention that we look at. If you look back at the other diagrams of the door, later on you'll see that it's always going to be that angle.
Okay.
All right? So the arm can exert less torque, and in fact, people who design machines for gyms have to take this type of thing into account when they're designing them, right? The human anatomy and its ability to apply torque. Let's have a look at another example of torque, this time on a compound wheel. This diagram is representing two discs which are fused together, one with the radius R1, the other one with the radius R2. We have equal magnitude forces being applied. In this case, we have a force of 50 newtons being applied perpendicular to the radial line. Do you see how this is being applied perpendicular to the radial line? In this second case, we have a force which is being applied at an angle of 60 degrees to the radial line. It's the same value force, 50 newtons. And we're asked to calculate the net torque on the compound wheel due to the two forces. So the force F1 acts to rotate the system counterclockwise, whereas F2 acts to rotate it clockwise. The two forces are in opposition to one another. So we've got to choose a direction of rotation to be positive. Let's say counterclockwise is positive, because that helps with our using our right hand rule, right? We could arbitrarily say we're going to have a left hand rule if you want, but it's better to do the same thing as everyone else in this type of case. So F1, force number 1, exerts a positive torque, which is given by the lever arm, R1, times the force. And the sine of 90 degrees is 1, so that goes out of the equation. F2 produces a negative or clockwise torque and does not act perpendicular to R2. So we're going to have to put in a factor of sine 60 degrees there. So we use a perpendicular component to calculate it. So we've got the torque number 2 is minus, because we agreed that clockwise was minus, the lever arm times the perpendicular component of the force, which is minus R2 F2 sine theta, with theta 60 degrees. So the net torque, remember we've got this sigma there, just like we did when we were doing Newton's laws, means the net force. Well, now we're talking about the net torque. The net torque is the sum of the forces acting. Lever arm times force number 1, lever arm times force number 2 times the component, the angle, taking into account the angle, so we get the perpendicular component of that force acting. So now we do the arithmetic here. 0.3 metres times 50 newtons, 0.5 metres times 50, 0.86. We have a torque of minus 6.7 metre newtons. That means that this wheel is going to accelerate in which direction?
Clockwise?
Clockwise, exactly. Because we had defined negative as being clockwise. And again, if we look at our right-hand rule, up is usually positive, right? And that's counterclockwise. Down is usually negative. That's clockwise. The two forces have the same magnitude, yet produce a non-zero net torque because their lever arms are different. There was really no way of telling immediately which one was going to be acting. If this angle had changed so that this was at 30 degrees, it probably would have been slightly the other way.